Yes, Professor, you can start.
Okay. So let me go to the lecture that I, at the point where I stopped yesterday night. Night for me, it was night for me, not for you, but for me it was night. And it was at the time where I discussed the point that the combustion chemistry is much more complex, is indeed complex chemical networks of elementary schemes, usually that are usually collision of binary collision of or some of them are ternary collisions. But it turns out, as I am going to explain to you, that it could be reduced to a one-step model, including the topic of the present lecture, which is the extinction limit. Oh my goodness, what's that? Okay. All right. Okay. So, okay. Where I am here. Does not work. Okay. Here, you know, the three, the reaction 1, 2, 3 that are reverse reaction on one way and on the opposite way, when all put together, they reduce to a one-step reaction, almost irreversible, to transform hydrogen and oxygen molecule in water molecule plus radicals with the speed, and this is the important thing, the rate, excuse me, not the speed, where is my pointer? Okay, with the rate of the reaction 1, you know, this, so this, in a sense, you can replace this shuffling reaction by a one-step reaction, which is written here, provided you assume that the reaction rate is proportional to the concentration of hydrogen atoms and oxygen molecule, okay, with a constant of reaction of the first reaction. Then this is a chain branching reaction because it produces a radical H or atom, H atom, it's not a radical, it's an H atom. It produces H atom at a speed proportional to the concentration of H atom. So this is going to produce a runaway of concentration of H. This runaway is contracted by the chain branching reaction, where you see this reaction 4F, 5F, 6F that are consuming the atom H by colliding with essentially with oxygen to produce, okay, it's hydrogen peroxide here, HO2, which is in the first step can be considered as an inert species. It is not the case. You see, these pyroxides are recycled by the reaction 7, 8, and 9F, you see. But to begin with, one can just consider that this is it's almost, the peroxide is almost inert. So in this, so there is a competition between the chain branching reaction and the chain breaking reaction, competing on the rate of production of H. And because the rate, the constant of the first reaction, excuse me, yeah, of the shuffling reaction, which is controlled by the first reaction here, this activation energy is large, and the other here has almost zero activation energy. This one has so there is, when you plot the constant of reaction versus the temperature, you have a crossover temperature. And this, above this crossover temperature that I define by T star, this reaction starts, but below for a temperature smaller, the reaction between oxygen and hydrogen does not start because the radical, not the radical, the atom H, which is an intermediate species, which is absolutely indispensable, necessary to go to water by combustion. This is consumed faster than it is produced. This crossover temperature turn out to be, this simplified two-step model with crossover is indeed valid also for hydrocarbons, more or less. But the difference is that there are some differences, but the main difference is that the crossover temperature, depending on the initial condition, varies between, let's say, 1000 Kelvin to 1400 Kelvin or 500, something like that. So this temperature is given by when equating the two reaction rate to the constant of reaction of the shuffling reaction and the chain breaking reaction. And it is clear that because this, when the heat is released, if the heat release is not sufficient to increase the temperature above the crossover temperature, this crossover temperature is purely a chemical kinetic data. It's not, has nothing to do with the composition of the mixture. It's purely chemical kinetics. But now the temperature of the flame, the burn gas temperature, which is this burn gas temperature, is depending on the composition. So there is a critical composition, which is written here, just to get an idea of how it works, that if you assume that the critical concentration, mass fraction, excuse me, of the reactant, which is oxygen here, is so small that the heat release, this critical value is just composition, is just defined by the crossover temperature. So for a crossover temperature, you have a well-defined composition below which, below or above which there is no flame. So this is the same thing. What's that? That's the same thing. All right. And this explains, in fact, this flammability limit that are shown here for the methane air flame, but it is the elementary physics is the same. The details are not the same, but the global history is the same. The history is the same. So you see, below this, for too lean mixture or too rich mixture, there is no flame. We cannot see any flame. Now, let's consider the case when you are near the flammability limit. What does that mean, near the flammability limit? This means that when you put together and when you include the reaction 5F here, you obtain for the, assume that everything is homogeneous in space, just to understand, you see, you have the time derivative of the concentration of the mass fraction of H, which is proportional to the concentration of H, with also the concentration of O2 because of this, and because O2 is here and also here. But with this difference, which is the difference of rate between 1 and 4F. But now, because you include the 5, this last reaction, you have an additional consumption rate coming from 5F. Now, this simplify appear if you assume, if you consider the case where this coefficient into the bracket here is small, which means relatively small to compared to one of the two elements at the critical condition. So this condition is a well-defined condition for the concentration. It is well-defined for at least for the temperature, burn gas temperature, for the composition. In that case, this term into bracket is small compared, not the term itself, but this term times CO2 is smaller than the NB5 B5F times CH square. And it turns in that case that you may balance the two and neglect the evolution of the H concentration. This is called a quasi-steady-state approximation. And in that case, it's easy. You have immediately, you express immediately the concentration of H in terms of the concentration of O2 and the ratio of these two rates here, which is written here. So, and below, so this is okay for T larger than T star, and for T below than T star is the temperature that is making this, the numerator equals 0 here, the concentration of H is 0. There is no possible of concentration of H cannot develop. And this, because now you can express the concentration of H, of the atom H in terms of the concentration of O2, if you put that in the equation, you obtain a one-step reaction, which is written here, where this is reduced temperature. When you are, the temperature is above T star, this reduced growth rate, yes, this reduced growth rate, GT, is the function of T. You see, you recognize here the bracket, and this is the last one here. So you have this, and below the crossover temperature, you have G equals 0. So now it's clear that you have reduced your problem, a multiple step chemistry, to a one step, including a crossover temperature. And you notice that the order of the reaction, which is the exponent of psi of the mass fraction of the radical of the atom H, is 2. So now, very close to the flammability limit, you can expand now this term in terms of because this is small, so this is 1 plus this, and so you can express that like that. So you can replace the term I don't know how you say it in English, T in terms like the inverse of the temperature, which is in fact the difference of temperature with the crossover temperature. And this is what is done here, very close to the flammability limit. You have this, and now your problem reduced to a one-step chemical, to one-step model of flame with a reaction rate, the temperature dependence on the reaction rate, which is simply a linear function of the temperature, of the difference of the temperature with the crossover temperature. This is valid above and below the crossover temperature. This should be 0. So in such a simple model, one can study, we can apply the same method, asymptotic method that we have used for the Arrhenius law and using the Zeldovich-Franz-Kamienski asymptotic analysis. We can do exactly the, not exactly, the method is similar here again is the equation written in terms of the reduced variable, the reduced temperature small theta, and psi for the mass fraction of the reactant. So when you you can look for the reaction zone as we did for the with Zeldovich-Frankamineski analysis. The method is the same. So I will not go through the detail. The students who are very interested to follow this can go back to the original papers, and which are mentioned, the references are well mentioned in my book, and so on. And so you obtain here's the final result, which was obtained by Norbert Peters at the end of the 20th century. So let's say 15 years ago. And this result is an interesting result. This is valid only for the burn gas temperature, which is defined by the composition and the dilution and the equivalence ratio of the mixture. So depending on this composition, this relation is valid only when the temperature, burn gas temperature, is larger than the crossover temperature. So you see what is what is surprising is that the flame velocity decreased smoothly to 0 when approaching the flammability limit. Flammability limit is the concentration that gives you a flame temperature which is equal to the crossover temperature. But this is not what is observed in experiments, you see, because in experiments you observe that the velocity is non-zero, is finite. It turns out that by the same, not only the velocity is decreased, but the sensitivity to the flame speed, the flame speed decrease, but also the sensibility of the flame speed to the temperature increase. So that it is similar in a sense to the case when the activation energy of the Arrhenius law increase. So that as I explained to you yesterday, the least heat losses quench the flame near the flammability limit. And this is why now this the flammability limit is contrary to what is predicted by the adiabatic case here, the flame speed is non-zero. You see, if I extrapolate here, I will have a flame speed here 0 for 0.5, something like that. It turns out that the flames, there is a thermal quenching before this, because the overall activation energy, if you, in a sense, is large. So this is this work, this result which was obtained. This is a very nice. Oh, excuse me. This is a very nice result obtained by Norbert Peters. You know, it's not universal. It depends on the composition and so on, but it gives you a good idea how the chemical kinetics can play an important role in the flammability limits. It turns out that the same method have been developed for methane flame by Peter and Williams in 87, and no, this was before, and also by Peter in 1997, and for the hydrogen-oxygen flame, you have an excellent review of Antonio Sanchez and Forman Williams in Progress in Energy and Combustion Science concerning the modelization of hydrogen-oxygen flame. Okay, this is the end of this the lecture. Now let me go to the next lecture, and the next lecture is I have to find the good files where it is. So this is the lecture. What's the number of the lecture? This is, should be 6. So I have to go to 7. Okay, lecture 7. Let me go. Is that right? Let me see that. Yes. In this lecture now, I am going to talk about a very funny phenomenon, which is called flame kernels, and a very important from the applied point of view phenomena, which is how to ignite a flame, for example. You see, and this is in particular for car running oils, and this is very important because in order to save the planets and to we try to use very lean hydrocarbon mixture, but the very lean hydrocarbon mixture, as you will understand now, are very difficult. Flames are difficult to ignite for such mixture that are good from the point of view of the pollution. So lean hydrocarbon flames are less pollutant than rich carbon flame. But the problem, as you will see, is that they are difficult to ignite. So the very important problem is that the flammability limits concerning planar flame, concerning the concentration beyond which planar flame does not exist, does not correspond to the critical condition for ignition. Some hydrocarbon lean mixtures that are flammable cannot be ignited, cannot be ignited at all in a quasi-isobaric manner. And on the opposite, some hydrocarbon-rich mixtures that are non-flammable can sustain curved flame. This is illustrated by the difference that appear in the between the upward propagation and the downward propagation of a flame tube concerning the flammability limits. So you know, the limit to propagate upwards with some cells, like it is written, sketch that as sketch. Oh, where I am, well, a sketch in this figure is quite different than when the propagating downstream. When not downstream, upstream, okay, upwards and downwards, so should be not stream. All right, this is a mistake. Okay, another very interesting experiment run by Ed Lowe, Professor Lowe in Princeton, concerning the turbulent flame, which are related to this point, that the turbulence facilitate ignition of hydrocarbon lean mixture, but suppress ignition of hydrocarbon-rich mixture. And this is associated with the phenomena I am going to explain now. The first important fundamental result to understand this phenomena is what is called the Zeldovich critical radius. It turns out that in spherical geometry, purely symmetrical geometry, there are steady state of premixed flame. So it's a premixed flame with a radius, a constant radius, standing steady, and it is fed by the diffusion of mass coming from the mixture from large radius, and the heat being extracted from the flame, from the reaction rate, by the diffusion. It turns out that in spherical geometry, this equilibrium does not is possible without motion of the flame front. This was realized by Zeldovich during the 1950, I guess, something like that. Because this comes from the fact that the Laplacian in spherical geometry is different than in planar geometry. This here as a Laplacian. And so that you may have an equilibrium between the heat conduction flux and the mass flux of reactant. I am working with, in this example, with a one-step Arrhenius law, one-step irreversible reaction, the simplest model, and with a large activation energy. So it turns out that you do not need a flow or an unsteady motion of in other sense of the front. So you may have a steady state solution. So this steady state solution, now what is important is that the temperature, the flame temperature, that is the temperature here of, this is a reaction zone here and here, and this is a premixed zone on both sides because the geometry is spherical. It turns out that it's easy to see when you look to this equilibrium here that the temperature is going to depend on the ratio of the diffusion coefficient. So it turns out that when you conserve energy, that the reduced temperature of the flame, which is defined here, which is T minus Tu is the temperature at infinity, Tb is the adiabatic temperature of a planar flame, okay, planar, this Tb, so you should understand that. Tb is the adiabatic flame temperature, which is written here, okay, for the planar. It turns out for this spherical flame, steady flame, and you will see it does exist. I will show you some experiments on that. So the temperature, the flame temperature, is depending. Where is my okay? Is depending on the Lewis number, the ratio dt divided by t here. So if the Lewis number, if the thermal diffusivity is more efficient than the molecular diffusivity of the limiting species, in that case, the temperature is smaller than the adiabatic. The flame temperature in this spherical solution is smaller than the adiabatic temperature of the planar flame, and it is opposite in the opposite case. So here is the equation, and now it's possible, you are not looking for the flame velocity because there is no flame velocity. The flame is steady, so there is no flame velocity. But what is important to find out is the radius. What is the radius of this solution? Then, so instead of looking for a propagation velocity, you are going to look for a radius of the solution. So in order to find out this radius, we are going to work exactly in the same way as we work for the planar flame. There are the inner structure is the same, indeed. You see the inner structure is written here. The thin zone when the activation energy is large. We have the same equation as in the planar case, but now we introduce the inner variables that are for the unity. For example, as in the planar flame, in fact, indeed, you see this big theta is for the unity. We are assuming that we are working in such a way that this term is of this flame temperature, reduced flame temperature. No, excuse me, this flame temperature. This flame this temperature, this reduced temperature is for the unity inside the reaction zone, and the space varies like the radius of the flame divided by beta. As it is the case in the planar, this is the flame thickness divided by beta. Here it is the radius. So let's go ahead. So here is the expression. I have written here the expression of the reaction rate in terms of the reduced temperature. And what you see is that you have when you introduce the reduced temperature that varies from 0 to infinity in this in the reaction zone here, when you are this rate become only theta exponential minus theta. The Lewis number is coming from the fact that the psi is related to the difference of the temperature through the Lewis number. You have the Lewis number, and here is a factor which is in front of this reaction rate because of this definition here. So, excuse me. Okay, now here is the equation that you have to solve. That's all. It's a similar equation as you already solved for the planar case, and using the same argument that we have used previously, you obtain that you obtain here the heat flux, the reduced form, which is leaving the reaction zone to preheat, to warm up the preheat zone where the reaction rate is 0. And then because you know exactly the external solution, because this is a very simple problem, which is given here, you just match the two flux, and you obtain now instead of obtaining the flame speed in the planar case, you obtain the radius of this steady state solution. So which is and the conclusion is the following: the radius is here. Divide dl is the flame. Dl is indeed the laminar flame thickness, planar flame thickness of the planar flame for Lewis equal 1. Okay, this is a reference length that is well defined, and tau b is defined as before, and so on. So now the results are the following. When the Lewis number is smaller than unity, this radius is smaller than the flame thickness, the planar flame thickness, and in the opposite case, it is larger. So now the question is, does this solution are stable or not? You know, okay, good. You find a steady state solution, but does this solution is this solution stable? That's a question that you have to do. It's not an easy task to do that. It's a little bit difficult to assess, but in fact, simple argument tell you that this solution should generically be unstable. Why? It is because, you know, when you look how the heat flux varies when increasing the radius, and how the convection, that in that case, when you increase the radius, in order to balance the diffusion flux is reduced, and in order to balance, you have to add a convective term in order to balance the reaction term. This means that, in fact, you have a positive feedback, which is going to be leading to an amplification of the least disturbance of the radius. So your solution that you And okay, good, very well, good, very nice mathematical solution. Unfortunately, it should be unstable. Okay, but it is interesting. This solution is unstable. But what you can show that when the radius decrease below this steady state solution, the radius go to 0. But when it is larger, it go above 0. So this radius, this equilibrium radius, steady state radius is in fact defined a critical radius for the quasi-isobaric ignition. If the quasi-isobaric ignition leads to a radius larger than the steady state radius, or you will ignite. It is smaller, you are going to you cannot ignite. And this is very interesting to notice that when the Lewis number is small, the equilibrium radius is very small, but when it is larger, Lewis number is larger than unity, this radius become larger than the planar flame thickness, which means, from an applied point of view, that lean hydrocarbon mixture are difficult to ignite. And this is why it is not so easy in car engine working with gasoline, gasoline gas engine. One has difficulty to ignite mixtures that are not pollutant. It turns out that this flame can be stabilized when you introduce heat losses, but this is a very difficult. I will not present the stability analysis because it is very technical, and I saw the people, the students that will be interesting. The analysis is difficult, by the way, it's subtle, but you have the original paper by John Bagmaster, Guy Joulin, Paul Ronet, let's say 22 years, no, 30 years ago. All right. And it turns out that such flame balls have been observed, such steady state spherical solution have been observed. It's clear that you cannot observe that on Earth. Why? Because you have the gravitation, and the gravitation destroys the spherical geometry. But in the space shuttle, experiments have been developed, and they have been designed by Paul Ronet from UCSD, in let's say 20 years ago, and showing this picture here this is what they observe, this kind of flame ball. So you see, that is very interesting experiments. Okay, it's not usual laboratory experiment because you have to go to be in microgravity condition in order to not perturb the spherical geometry. It turns out that this analysis has been also extended for the initiation problem when you have a constant energy source, but I will not enter into this detail. What I would like just now to present to you is what happened near the flammability limit, because up to now, I have discussed the case of the Zeldovich solution, spherical steady state, with Arrhenius, with one step governed by an Arrhenius law. In that case, there is no flammability limit. Now you can use easily the models that I have discussed, that I have presented previously, where you introduce the flammability limit. And I am going to present not the detail of the calculation, but just an overview of the results. What you have to keep in mind is now that you have three different temperatures. One, T star, is a crossover temperature, which is purely defined by the chemical kinetic. It is a chemical kinetics data. It has nothing to do with the composition. TB is purely, which is the adiabatic flame temperature of a planar flame, is completely defined by the composition, because it is defined by the heat release, which is liberated by unit mass of mixture, and this depends on the composition, clearly. And now you have another temperature now, which is the flame temperature of Zeldovich solution, which is TF, such that the reduced temperature is varying like one another. So you have to discuss now the Zeldovich solution when you are close to the crossover temperature. When TB is close to when you are close to the crossover temperature. Let's just say that here are the equations, the same. There are that I have presented before, but here they are written in reduced variable, and the small parameter epsilon here that you have here, excuse me, no, it's this one. Where is my pointer? Ah, okay. You know, this small parameter, which is defined here as the difference of the adiabatic flame temperature minus the crossover temperature amplified the difference by the reduced activation energy, which is a large number. This number is going to be for the unity in our analysis, and it defines the distance from the flammability limit. When you are the flammability limit, it is 0. When you are far from the flammability limit in the burn, when you have a flammable mixture, epsilon could be very large. Therefore, now you redo the same calculation as before, but now using with this epsilon of all the unity, which appear here in the reaction rate. Okay, so here are the detail, but you can skip this detail. Simply keep in mind that the reduced crossover temperature here is in fact related directly to this small epsilon term. Okay, so this theta star and epsilon are equivalent in the sense they are related linearly by this simple relation here. This is, it turns out that now, when you looked, you have a beta cube. The main difference compared to the problem of the planar flame, adiabatic planar flame, is that now you have a beta cube term in front of that, in front of the, in front of the reaction rate, and then you have a reaction rate which is a difference like that. So you multiply by d theta over dxi as we did before, and so on, and and you do that, and you obtain the heat flux as usual at the exit of the reaction zone, and you compute the same this, and now a simplification occurs if you are considering condition when you are close to the flammability limit, so that this term, this theta f here is here, and so you can develop the production rate in terms of theta f, because this theta f is close to unity when you are is close to zero when you are close to the flammability limit. And okay, let me skip the detail, and then solving the preheated zone, matching the preheated zone with a reaction zone, you obtain this expression here for the radius. And it turns out that this expression, that, you know, the radius, which is in terms of, in a sense, it is the inverse of the radius divided by the thickness of the adiabatic flame. You see, depend on the Lewis number and of this G term here, which is here as it is. So now let me show you what are the results. So you have the temperature Tb defined by the composition of the mixture. You have T star, which is determined by the chemical kinetics. And now let's consider first the case of Lewis number larger than unity. In that case, Tf, the temperature of the Zeldovich solution is smaller than the adiabatic temperature, and there is the composition for the flammability limit is defined when you arrive at for a temperature equal to Tb, but the flame kernel correspond, the steady state flame kernel correspond, the limit of the flame kernel correspond to a concentration which is smaller, in such a way that in that case, the flammability limit, which is here for the composition, is below the existence of a spherical steady state. So there are conclusions for Lewis larger than unity. You have, you have a range of composition where the mixture is flammable for a planar flame, but you cannot ignite that by a spherical adiabatic case, a quasi-steady adiabatic case, because the radius is infinite. The radius diverge at this concentration. So here you find now, excuse me, okay. So this is the case for heavy hydrocarbon, Lie mixture of heavy hydrocarbon, or for a rich mixture of hydrogen. But in the opposite, when the Lewis number in the opposite case, it is just the opposite. You have spherical Zeldovich solution, radius, that exists for concentration that are below the flammability limit. So when you have flammability limits, keep in mind that the flammability limit are just defined by the planar solution, adiabatic planar. So you see, you have, in that case, you have non-flammable mixture, in this range of concentration, non-flammable because the flammability limit is here, that can be ignited spherically. Or let's say that in that case, you have the existence of flame ball. And And this is the case of lean mixture of hydrogen lean mixture. And this is exactly the condition used by Paul Ronnet for the experiment in the shuttle, in the space shuttle. Okay, so for the same reason, you know, when on Earth, when you take into account the gravity, the gravity force, upward propagation is possible in non-flammable mixture because of the steady state, because of the solution of the spherical cap here, the temperature is larger than it is for planar. So you cannot propagate a flame. The composition is such that you cannot propagate a planar flame, which is the case because the flame velocity is small for downward propagation, but you can propagate upward. So in a sense, this is an important problem for safety because buoyancy promote curved flames and promote combustion of mixture that are non-flammable when considering only the planar case. Okay. A simple explanation of how the turbulence can influence the initiation of flame is that, you know, turbulence, contrarily to laminar things, has a diffusion coefficient. All the diffusion coefficients are controlled by the turbulence, and so the Lewis number, the overall Lewis number or effective Lewis number in turbulence can be considered to be one unity. Such a way that you see the difference between Lewis for Lewis larger than 1 or Lewis minus smaller than 1 that we have discussed, in fact, disappear. And so it changed completely. The turbulence can change the criterion of initiation. So this is a delicate problem, which is not completely completely understood, but it deserves a lot of future work. So let me go now to close this this chapter to another problem, which is also relatively difficult to understand from a mathematical point of view. It's really a delicate problem. Let's say a very interesting problem because mathematical problem, but not easy to follow. The question is the following. Can we use the quasi-steady-state approximation in the Premixed zone or in spherical geometry? And it turns out that there's the relation time to the steady state profile here, which is this relation, you know, when you have a radius, it is r squared divided by the diffusion coefficient. When the, you know, quasi-steady-state approximation, which will be useful if you can neglect this unstudied term here, is possible if this relaxation time toward the steady-state solution is much smaller than the evolution time. It turns out that this can never be the case at large distance. So this was noticed by Guy Joulin some years ago, and if it turns out that there is an exact solution of the heat equation when you have a point energy sources and where you have where the heat you have a rate of non-zero rate of heat release at a point. right? And this is if you solve the purely this is you solve it, the Fourier equation for the it, you obtain the solution, which is in fact the profile of temperature with the radius versus time for when you know the function, which is the source term, which is assumed to be punctual but time dependent, and you have this, and this is a solution. And you obtain this solution, and the relaxation time toward this steady state increase with the radius, like r squared divided by dt, so that it is clear that at large distance you cannot be quasi-steady. So now, say in another way, this say that the dynamics is going to be slaved by the far field, where the radius is large. Okay, so this is I will stop for 10 minutes here at that point, and we will continue this presentation in 10 minutes. Okay, thank you.
Thank you, Professor.
Okay. You can stop the recording. Therefore, good. So let's start again the lecture. So my conclusion at the end of the first hour was that all the dynamic is controlled, in fact, by the motion in the far field. And so and this problem was completely solved for Lewis smaller than unity and near the Zeldovich radius. The slow motion of the flame kernels, a solution for this slow motion was obtained by Guy Joulin, and the equation he obtained is for the radius, which is the ratio of the radius divided by the Zeldovich radius here, which was given here. So it turns out that, so as we said already, it is unstable, but you have the way that the radius increase, either it decreases when the radius is smaller than the Zeldovich radius, or it increases, showing clearly the problem of initiation. In order to initiate, you should start with a radius which is larger than the Zeldovich radius. So this solution was extended later on by Guy Joulin with an unsteady energy source, and he obtained this kind of picture that, excuse me, that you have here. You see when the initiation source is sufficiently powerful, you cross the Zeldovich radius, and then following this analysis, you ignite. But if the energy source is not large enough, you cannot reach the Zeldovich radius, and you never ignite. So even when the energy source is so this depends on the intensity of the energy sources. And so you have this picture, and it turns out that this was used by the engineer in the gasoline engine to understand. It was also interesting that work I did later on was to explain the dynamical quenching of flame kernel in non-flammable mixture. But I will not. I will just say that it's possible to extend the analysis of Guy-Joulin to describe this phenomena. This phenomena of self-extinguished flame in microgravity experiment of clean methane air mixture. This was observed by Paul Ronnet. So now we are going to change topic. The next lecture is the lecture 8. Where it is? Okay, here it is. Okay. Okay, we are going now to analyze an interesting topic concerning thermo-acoustic instability and what is called the vibratory flames, phenomena of vibratory flames. Let's start with the Rayleigh criterion, which is a famous criterion that was for the instability of a combustion in a cavity, which was obtained in the 19th century by the famous physicist Lord Rayleigh. So it is an interaction, you have to take into account the interaction of acoustic wave in a reactive medium. You consider an ideal gas law, so as usual, so P equals Cp minus Cv rho T. And now if you compute dP over dt and you multiply by Cp over Cp minus Cv, you obtain this expression here, which is by applying the Lagrangian derivative. And the Lagrangian derivative is written here. Excuse me. Where is my pointer? Oh, okay. The Lagrangian derivative is written here. Okay. Introducing the sound speed, which is square time this expression here, you may write, excuse me, this equation here like that by putting the temperature on the left-hand side. And by expressing dρ over dt in term by introducing CPT here and introducing A square for CPT. The energy conservation equation, which is that I have recalled in the second lecture, where appear here, excuse me, where appear the pressure term on the right hand side. Here you cannot, this pressure term was suppressed when we are considering quasi-isobaric propagation. But here, because we want to discuss the interaction with acoustic, it's out of question to do not consider this term. So putting now the energy equation with this equation coming from the ideal gas law, you obtain, by eliminating the temperature, you obtain this equation written in red here, that can be written in that way, where the Lagrangian derivative of the pressure here minus A square, the Lagrangian derivative of the density, is the rate of it, the rate of it produced by unit volume locally. And this rate, in general, you have two terms. You have the coming from the heat transfer and coming from the chemical reaction. You see, it turns out that we are going to use essentially the second, this term, and this term has to be taken into account for to obtain details, but generally speaking, you can forget about this term and consider this effect here. And we use an isentropic law. So here are the equations written again. And what we are going to do is to linearize. You assume that you have I will essentially use a one-dimensional system, uniform, okay? So the unperturbed state is uniform, and the reaction rate is the combustion is distributed uniformly in the, it is a tube, because it is, if you are working in one dimension, it is a tube, all right? When you neglect the mean flow velocity in front of the sound speed, you obtain this relation here, telling you the relation between the derivative of the time of the velocity and the gradient of the pressure, and using the relation, taking the second derivative of that, you obtain the equation on the following equation, which says that the following. On the left-hand side of this equation, you have the equation for the acoustic wave. You see? Yes, 0 is acoustic wave. And then on the right-hand side, you have a source term, which is coming from the heat release, which is, excuse me, which is here. This term is here. So this is a heat release. You have a gamma minus 1 heat factor because of the compression effect. So if you eliminate now the density, you obtain on the left-hand side using this equation here, you obtain on the left-hand side the acoustic waves. Here it is not one-dimensional, it's general. So you have acoustic wave, and these acoustic waves are fed by the heat release rate, which is by the time derivative, is the power of it, like that. So this is a simple equation that you obtain by considering, by linearization, an homogeneous reactive flow, and if you the pressure P prime now should be computed in a cavity, and where you have the and leading to the acoustic waves. Okay. And now let me just recall a classical problem of sound emission by a localized heat source in free space. Now, when the acoustic wavelength is much larger than the size of the combustion zone, so you may you consider that in that case the source term, which is here, is a delta term in space and depend on time, and the time depending here is the integration on space of Q dot, which is the heat, which is here. So using the green, maybe some of you know that very well, others do not know, forget about if you don't know. There is what is called the Green's retard propagator, which is solution of, excuse me, where is my pointer? Okay, this now if you take the same equation here, putting G instead of P, but now putting a delta function in space here and time. You put, you know, is a response to a local instantaneous heat release. So if you use this, you obtain the general solution. Using this solution is written here, is a retard function divided by the radius. We are in spherical geometry, and don't forget that. And the pressure can be obtained easily in terms of the heat source, which is written here. So this is just a classical result of acoustics. Now, let's try to understand simply why, when and why an homogeneous combustion in a vessel become unstable when it is coupled with the acoustics. The reason is a loop that is written here. Unsteady heat release generate sound wave, generates sounds, and this acoustic wave counter-react to the heat release rate, and this can produce a positive feedback, so that, for example, a very old experiments by a man called Higgins in England or Great Britain, I don't know, it is in England, called the singing flame. What is it? You take a Bunsen burner in a tube, and depending on the position of the Bunsen burner in an open tube, okay, the tube is open on both sides, okay, and you have a Bunsen burner inside. Depending on the position, you excite the acoustic mode, and you see that the flame vibrated with the frequency of the acoustic mode. People at that time thought that this was a chemical effect, but it turns out that it is a simple effect of coupling between the heat release and the sound generation. And later, there is a very famous experiment called the rigid tube, where the same, but you have hot wire that you displace, that you position, you look for the position, depending on the position of this hot wire. For example, this hot wire is warmed up by conduction, electric conduction, for example, and you displace, you change the position of this hot wire, and for some position you excite the sound wave, you hear the sound generated. So this is a sound which is generated by the heat release. This instability here, this coupling between combustion and acoustic wave is a nightmare of the engineer building rocket engine or also gas turbines, because it leads to very, very strong instability that can destroy the rocket or the turbine. So strong that so let me start with the simplest, retroaction mechanism, this one here, which is in blue here. Here. You know, this retroaction here through the pressure coupling. Say that when you increase the pressure, you increase the heat release rate, you see? And for dimensional reason, because this is an energy per unit volume and unit time, when the pressure, when fluctuation of the pressure should be divided by the time. And it turns out that when this term B is positive, these times that appear here for dimensional reason is in fact the characteristic time of the instability. Let's work with to begin with, in one dimension geometry in Fourier space. That's for in Fourier space. Every component, excuse me, every component, the Fourier component of the pressure obeys according to this equation to a second order. This is depend on the P tilde, depend on the wave vector K, depend only on T. Now you are faced to an ordinary direction, second order differential equation, and so it is very simple to solve that. So you can immediately, to understand what happened, this is an exercise for undergraduate student. You look for solution in normal mode, exponential theta, put this decomposition in. You have now a second order algebraic equation for sigma. Here is the solution. And now work in the case where this AK is a square of the frequency, okay? Acoustic frequency, okay? This is a square of the acoustic frequency, and work in the case where this acoustic frequency is large compared to this number that characterize the coupling between the pressure and the heat release. Assume that you are working. This is a very good good approximation in ordinary conditions. Now you end up with a sigma, which is B and plus or minus, and this is a negative, so this is a frequency, but you have a real part B now here. And, oh, excuse me. Wow. I did something wrong. Okay, with my, okay, here I am. Now it's clearly the real part of the growth of the complex growth rate. Where is, okay. According to this equation, is B divided by tau instability. If B is positive, it's clear that the fluctuation of heat release and pressure are in phase, and in that case, you have an instability. So as soon as the heat release, the heat release fluctuates in phase with the pressure, you have an instability. This is what this was obtained. This is called the Rayleigh criterion. And in the opposite case, you are stable. Now, when you are facing with a real problem, you have a delay, indeed, between the pressure and the heat release. For example, you can understand that if, for example, if the combustion involve droplets of hydrocarbons that vaporize, so you have a delay in the vaporization or in delay in the injection. So the general law relating for the pressure coupling, relating the pressure to the heat release is not a simple law with a real number here, B, positive or negative. It is you go through a form like that, and now it turns out the result is the following: if the phase lag is between minus P over 2 and P2, you are in stability. It's quite understandable. It's very simple, and nonlinear study can be performed in that case. And in fact, you find out limit cycles so you find a oscillation at finite amplitude. It's the classical problem in combustion in a closed vessel. Okay, the vessel is closed for the acoustic. It's clear that the vessel cannot be closed because you have to feed the combustion with oxygen, and you have to leave the product to get out. The closed, when we talk of combustion, when we talk about a combustion in a closed vessel, the closed vessel is for the acoustic wave. For example, when you have a rocket engine and you have a nozzle, the nozzle where the gas through which the gas exhaust is exhausted, this nozzle acts in fact like a solid wall for the acoustic. So this is okay. Let me now go further in this thermoacoustic instability by introducing what is called admittance and the transfer function. We start with a very simple experiment that I have mentioned already. That is a flame propagating in a tube, right? And assume that the thickness of the flame, now you have a flame brush. You see, your flame, usually in a tube, is not planar. So you have a flame brush, okay? So it is better to talk about the flame brush instead to talk of just a flame. So assume that the thickness of the flame brush is larger than the acoustic wavelength. So your acoustic wavelength is characterized by the length of the tube, and assume that the thickness of the brush is it is just the opposite. Excuse me. So there is a mistake here. It is just the opposite. The thickness of the flame brush should be small compared to the acoustic wavelength. Excuse me, there is a misprint here in my slides. I will correct that later. Where is my pointer? I do not, my pointer. Okay, so this is just the opposite. The thickness of the flame brush is much smaller than the acoustic wavelength. So in that case, all the flame can be considered like a discontinuity for the acoustic wave, okay? And because of the gas expansion, there are jump of the fluctuation velocity. You see, okay, when you assume that the acoustic is one-dimensional, so you have here a combustion, a flame brush, and called delta U, this is a fresh mixture, this is a burnt mixture, called delta U, the longitudinal fluctuation of the velocity in the fresh mixture, and delta B, the longitudinal fluctuation of the flow velocity in the burn gas on the burn gas side of the flame brush. Typically, this difference of velocity fluctuations is of order of the laminar flame speed. So this gives you an order of magnitude of what we are considering. No, excuse me. So now considering the pressure jump across the flame brush, this pressure jump is of order, the relative pressure jump is like in flame, in fact, is of order of the Mach of the propagation velocity of the flame divided by the speed of sound. So this is a very small number. So you can consider in a first order that there is no jump of pressure. There is just a jump of velocity across the flame brush, but no, you can neglect the jump of pressure in such a way that the acoustic problem that you have to solve is relatively simple. You have a fluctuation of the pressure on the flame brush and a jump of the velocity, of the fluctuation of the velocity across the flame brush. All right. And now it's consider, for example, in order to understand this equation here, consider a tube with a closed end that is vibrating, like a loudspeaker. You see, assume you have a wall, a wall of the tube is closed, the other is open or closed, and this is no problem. And let's oscillate this wall, and call delta U the fluctuation of the wall. So it is clear that the acoustic energy is delta U times delta P. This now, because now you have this difference of pressure of flow here. Where it is? Excuse me. Okay. Okay. Because of this difference of velocity, now you see in one side you are compressing, in the other side you are expanding. So you should have the difference, the energy, which is the average period of oscillation, average flux of combustion energy, which is transferred to the acoustic wave. There is no R, excuse me. So this, another mistake, but this is not very important. Transfer to the acoustic wave is just the average of the difference of the fluctuation of the velocity multiplied by the pressure. But because of the mass conservation, assuming that the flame brush is quasi-isobaric, you have the divergence of the velocity, which is equal to minus 1 over rho d rho over dt, which is 1 over t dt over dt. And this is simply the heat release rate divided by rho a square. A is the sound speed. So in this equation here, you have this expression, you have to introduce this expression. And now, you know, when you introduce this expression here, in this equation, you obtain the flux of combustion energy, which is transferred to the acoustic wave during one period, if you average during the period. Okay, so it's clear. This is simple, very simple. Now, I have recalled the result here. And there are two mechanisms of coupling. The first is the one already discussed by Rayleigh, which is called the pressure coupling. But this now pressure coupling, I am discussing the pressure coupling not with an homogeneous reactor, but with the flame brush, which is a different story. But you will see that the analysis is finally not so different. Now, okay, so let's introduce the Fourier decomposition of U in terms of you know, at the flame, the Fourier decomposition and the Fourier decomposition of the pressure in such a way that one introduce with the hat, the quantity with the hat is it's called the Fourier transform in time from this time, from this. So now, what you have in the pressure coupling is that this frequency, this Fourier transform of the pressure is related to the jump of velocity through a complex factor. And this complex factor is the definition of what is called the admittance. And this clearly depends on the frequency. So this relation here is the generalization of the relation, linear relation used by Rayleigh for the simple pressure coupling. So now this is a definition of the admittance function. So you have to compute this for any flame and so on, but at least you know what you have to compute. Now, you can compute easily when you know this admittance function. You can compute the energy which is transferred from the combustion, from the flame brush, indeed, to the acoustic mode, and you obtain this expression here. Okay, like that. You have to sum over all the frequency, but just for the moment, consider a single frequency. Assume that it is, for example, the fundamental mode of the frequency, and so using this, you obtain this expression. And this is the expression generalizing the expression, the simple expression used by Rayleigh. It turns out that this problem has been solved for a planar flame. We solved that, for planar flame, and here is it is an exercise, a complicated exercise, but it is straightforward in a sense. As soon as you know already the general picture of the thing, but now you have to compute this. This can be computed, for example, for a planar flame. For a planar flame, the pressure, but it turns out that this pressure coupling is weak, because because of this you obtain when you solve the problem. It depends on the frequency, no doubt about that. Here, you have this term here, because the Mach number is small, because gamma minus 1 is not large, it's 0.3, 0.2, 0.4, and this is 10, but this number is smaller, much smaller than unity, in such a way that the coupling is weak, and in such a way that the gain for the instability is in fact relatively small, and it is damped out by different losses that you may have, for example, because the acoustic energy is radiate out in the environment, or because you have viscous dissipation and so on. So this instability for a planar flame is difficult to observe, the pressure coupling. Okay, so however, a more interesting thing is written here. You see, assume you have a solid propellant, and which is for a one-dimensional case where the tube, the end of the tube is a solid propellant, and this solid propellant burns. Also, you have a closed end of the tube, which is a solid propellant burning, and this solid propellant, which is burning, excuse me, where I am here, for the same, by the same argument that are developed here, you can compute this velocity. Now you have only delta U plus, you have only delta U B, and you do not have delta U minus, because there is no fluctuation. So this is going to fluctuate, and this is acting because of if you have a real part, a positive real part of the admittance function, this is acting like a loudspeaker. And it turns out that this was considered by Zeldovich very early, but he was considering the combustion inside the flame as quasi-steady. And it turns out that this is completely wrong, not completely wrong, but not useful. And that much more dangerous is the fact of the unsteady dynamics of the frame structure. And this, and the transfer function, and the admittance, excuse me, it's not the transfer, the admittance function that you can compute here depends strongly on the frequency, and it turns out that you are more unstable at high frequency of the tube. Shorter is the tube, then longer is the tube. And this has this has been used by Linian and another one to study the instability of real solid propellant, when in fact in a real solid propellant, just let me tell you what the situation is. This is a wall. So you have let's say a wall on that side, a wall on the other side, a closed tube here, and on the other side you have an exhaust, the gas exhaust. And it turns out that the acoustic now, the problem with acoustic is complicated, but it turns out that this velocity here feed, excuse me, the longitudinal modes, and you obtain, but it's the problem is more complicated because you have also tangential modes, because if it is a cylinder, you have also acoustic modes that are tangential, longitudinal modes, but now with such a response function, admittance function that is computed here for ordinary solid propellant, you may have a very strong instability of the rocket. Okay, now let me go to another coupling which is more important for the gaseous flame propagating in a tube. As I told you just before, the pressure coupling for gaseous flame is not important. The pressure coupling could be important for solid propellant, but for acoustic is not very important. So there is another coupling which is important, and it is written here. Now you have to consider a flame brush. It's no more, you can, now you have to consider a flame brush, and a fluctuation of the velocity field modifies the flame geometry. So it modifies the flame surface, and this is modification of the flame surface is going to modify the quantity of heat which is released, because the quantity of heat which is released per unit time depends on the flame surface. If the flame surface is fluctuating with the pressure, with the velocity, now you are going to make the delta U fluctuating with the velocity. And you define now the transfer function for a flame in a tube, which calls this TR now, by the difference in the frequency representation, that working in the Fourier space, time Fourier transform. So you define the transfer function now relating the fluctuation of one the fluctuation of the velocity of one side to the difference of velocity. It's clear that if there is no difference of velocity, so you have just a flame that is moving back and forth without injecting energy in the acoustic. said in other words, the difference of velocity acts like a difference of as a fluctuation of volume, you see? So this is like a loudspeaker. Okay, so now this is the definition of the transfer function in the tube. Okay, forget about the detail. And now let's forget about the detail. It's not necessary. For a weakly curved flame, it turns out that the surface is just which is sketched here. So now the heat release, the fluctuation of heat release integrated across the flame brush is simply proportional to the increase of the relative increase of the surface of the flame divided by the cross-section area. So using now this relation, you obtain very simply the transfer function as soon as you know delta S in terms of delta U. If you know the delta S into delta U, now you have this relation here. I will not enter into the detail, and I just would like to tell you that the equation you have to consider is a second order differential equation that I have obtained for a flame propagating in a gravitation field. Now, when the flame what is interesting is that when the flame is in an acoustic field, the gravity that you have to introduce in the equation that I have described for you here, this gravity now is oscillating because this is the acceleration which is produced by the acoustic. And so you have this, and the transfer function has been computed for different frames by this. And it turns out that it is really what happened for the primary instability in a tube. So in order to understand that, let's be back to an experience that I have already mentioned, which is called the vibratory instability of flame. You know, remember what this experience, when a flame propagates, in the tube, depending on the composition, may have very strong effect. In the first, as you see, in the first stage, the flame becomes quasi-planar, and suddenly, you have a different regime, and this second regime here. So the primary regime instability is the one I have described, and the second instability is the parametric instability, which I just want to mention without giving you details of the calculation because it is too much complicated. Let's say that in the first, as a first step, you can either stabilize or destabilize the flame with this oscillatory instability. This is the first. This is the important point. Here are the equations, but forget about, and simply recall, keep in mind, when the flame propagating is propagating downward, you may have a range of unstable due to the Landau instability or wavelengths here. And the generic, the archetype of the equations that you have to solve here, except for this damping term here, is this term where you have a second order derivative with respect to time, and proportional to the y, to the yt, but with a square of the frequency which is oscillating in time. This is a very funny problem. This is called the Kapitsa. It's called the Mathieu's equation, and was used and it describes two very important phenomena. The first one is called the parametric instability discovered by Faraday. For example, when you have let's say a recipient filled with water, and you make this recipient oscillating in the z direction. That is, you oscillate this. What you see in that case, you see that cellular structures that appear on the interfaces separating the liquid from the air. And this is called, this was discovered by Faraday, and it's called the Faraday instability. So, and it turns out that this equation, not depending on the condition, describe either an instability or a stabilizing mechanism. For example, a very spectacular phenomena, mechanics phenomena, is Kapitsa, was discovered by Kapitsa. You see in this picture on the right here, yes, you have a plate, a flat plate, and this flat plate, you make it oscillate, all right? And here you have a pendulum. It turns out that if you adjust with sufficiently, let's say, you adjust that at the right frequency, you can stabilize a solution that usually are unstable. Well, you see this with an angle here, if there is no oscillation, the pendulum goes down. No, but if you put this pendulum in a frequency correctly adjusted, you may stabilize this. So this is just to point out that the Mathieu equation, which is the archetype of the equation for the flame propagating in a tube, in a sense, is describe a very complex situation. And you see, here is the frequency, and here is the amplitude. You see, frequency is on the horizontal axis, and amplitude is on the vertical axis. This is the amplitude of the oscillation, and omega is a basic frequency. It turns out that you have tongues of instability here. You are unstable in the gray region, and you are stable in the gray region. And this is exactly the same things occur for the flame when you take into account now this more general equation than this Mathieu equation, which is the equation. This equation was derived very early by Mach-stem indeed. And it turns out what I have shown here is that depending on the amplitude of the acoustic and depending on the wave number that is associated with it, you may be either unstable. For example, in the gray region here, you are unstable because of Darrieux-Landau instability, but in this gray region here, which appear for a finite amplitude of oscillation, now you have parametric instability. This has been verified by very, very good experiments. And this also can explain what I present at the beginning, the flattening of Bunsen burner by an acoustic. So this is just to give you an overview without too much details of the problem of the interaction between acoustic and flame. Okay, it's time to have a 10-minute breaks now, and we start again in 10 minutes, right? Could you stop the recording? Mm-hmm.
Yes, Professor.
Okay. Good. Okay, now the next lecture is concerned the turbulent flames. Before beginning this chapter, I just want to tell you that the theory, there is no real theory for turbulent flames. For example, but it is the situation is even worse because there is no fundamental theory for the non-reactive turbulence. So you know how. So the situation is even worse with the turbulent flame. So I will limit my presentation to some very simple ideas and half idea, and I will, because I do not believe in the different modeling that is used in the engineer activity for turbulent flame. This is not very good because most of the application of combustion in industry are turbulent, but unfortunately we do not have a real theory for turbulent flame. So you know, the problem of premixed flame in turbulent flow is still widely open. For example, here it's there is a sketch of a flame. Oh, where's my okay? A wrinkled flame, which is wrinkled by the turbulence, propagating in a tube. All right, and the question is, what is when you know the characteristic of the flame brush, the turbulence-induced flame brush? Could you say something interesting concerning not only the propagation on average of the front turbulent flow, but also could we say interesting things considering the thickness of this flame brush? As soon as you know the turbulence, for example. Situation is very difficult because the experiments are difficult and the data, experimental data, are very scattered. So there is no real theory for that. And for example, if you consider the simplest model, mathematical model, which is written here, which is, you know, if V, if you suppress this term, you have the flame problem with a Lewis number equal to unity, the propagation. Now, if you prescribe a turbulent stochastic field in factor of the gradient here, which is a flow, a fluctuating flow in front, and assume that the flow is not modified by the combustion. This is surely not the case. But even this very simple problem, where this flow, turbulent flow, is prescribed, is a stochastic field which is prescribed, there is no result concerning this problem. Not only, let's say that, I will be back to that, the very existence of the increase of the flame surface, or let's say an average, a steady state, assume that your turbulence is steady state. And the question is, does there exist an average, a steady average surface of the flame, and also, does it exist a finite, a well-defined and constant average thickness of the tall brush, even the very existence of this quantity is quite questionable. There is no answer for that. The only thing that one can say, and if we neglect the modification of the flame structure by the stretching or by curvature, even in that case, you just by conservation of mass, you can say that the turbulent propagation will be simply the ratio of the increase of the surface by the divided by the cross section of the tube multiplied by the laminar flame speed. This is a general result which is exact, but when you do not know the average flame surface, you don't know anything. But this relation here is exact. And the only exact result that was obtained is when the fluctuation is small, the velocity is small compared to the flame speed. You know, when this term here, V, the modulus of the amplitude of V divided by the laminar flame thickness is a small quantity, like here it is written. In that case, you can show it. Let's say you can show almost rigorously that the turbulent flame speed is quadratic in terms of the increase of the ratio of the velocity, turbulent velocity divided by the laminar flame speed. This has been shown, has been conjectured by Shelkin very in the middle of the 20th century, and we have a full description of this problem with Foreman Williams in the 80s. So the opposite limit, in fact, maybe is the most useful one. That is when the intensity of turbulence, that is the amplitude of the fluctuation of the velocity of the flow, is much larger than the laminar. In that case, a good argument tells you, and I will come back to that, tell you that the turbulent flame speed is simply the intensity of turbulence. In fact, it's simply the V, the fluctuation, the amplitude of the fluctuation of the flow, on average. All right. So there are very few things that one know about turbulence. Let's go to what is called the turbulent diffusion, and it's interesting just to know the result by Taylor and Einstein. In fact, when you consider the following, you have a turbulent flow, you put you want to know how inert particles are diffusing in a turbulent flow. This is a question you ask. And in a sense, you want to find out what is the diffusion law of a contaminant in a turbulent flow. This is a very important problem in many applied situations. Consider for simplicity the one-dimensional case. So you have a fluctuating velocity, flow velocity here called VDT. You have, let's say, a Lagrangian displacement xt here. You can compute the square, the average of the square of this, and this is related if V is a stochastic Lagrangian function. Let's say it is a stochastic flow velocity depending on time. Now it's clear that when you average this quantity, you have to take into account this correlation function here, and you have this this equation can be written in that form, and assuming that the turbulence is homogeneous in time, which means that the correlation function does depend only on the difference of time between the two velocity here. G is called the structure function of the turbulence, and it is proportional, and this divided by the average of the square is called G de tau, and this G is a decreasing function of time, usually which is monotonous, a decreasing function of time, and using an integral by part from this equation, you obtain this form here for the quadratic displacement of the passive contaminant. And if you assume that, and considering that this integral, this integral here is proportional to the intensity, to the square of what is called the square of this integral here, which is called the integral time of the fluctuation, and assume that this integral is of order, is constant, is finite, and of order of the integral time square, which is, and this is true when t is much larger than the integral term, so that g goes to 0 when t is sufficiently large. So in that case, you obtain the same formula as obtained for the random walk, and the coefficient that you have in the displacement square increase like the time, linearly in time, with a coefficient, and this coefficient is related to is of the order, or let's say, this is say equivalent, it is not quite exact, is of the order of the intensity of the turbulence square multiplied by the time, integral time here, which is the, the integral of the structure function of the turbulence. So this gives you, notice first that this equation here, for the diffusion, turbulent diffusion, is correct from the point of view of dimension analysis, because the diffusion coefficient should be a velocity square time a time, multiplied by a time. Good, so this is what is called the Taylor diffusion coefficient, which is an analog of the Einstein random walk for molecular diffusion, in fact. That's all. Simply, you replace the random walk due to the collision by the random walk due to the fluctuation, velocity fluctuation of the particle. So the Roth model for the turbulent is to say that simply by analogy with what happened in Laminar, that you write that the correlation between V, the flow velocity, and the scalar, here it is a reduced temperature, for example, is this is the flux, that this flux, fluctuating flux on average, you say that it should be of the order of this dt turbulence time gradient, so that the divergence of the divergence of this flux is like in molecular diffusion, is associated with the Laplacian of the scalar multiplied by the diffusion, turbulent diffusion. All this. All these models are very limited, and this turbulence, saying that is of order of what is called an integral length times the velocity, the amplitude, the fluctuation, the fluctuation of the turbulence intensity, turbulent intensity times the length associated with the correlation length here, which is here. It turns out that all these models are, let's say, very bad. They do not work very well, and one can say that even though they never work at all. There is another limit for the turbulent combustion which was considered in the past called the well-stirred flame regime of Dampf-Köhler, where the integral length characterizing the correlation function of the velocity field is much smaller than the laminar flame thickness. And this well-stirred flame regime, which was considered by Dampf-Köhler, is never realized. I don't know any example of maybe in astrophysics inside the star, but even though I am not, nobody knows exactly. But this is not very very useful. Now, let me just present briefly what is called the strongly corrugate flamelet regime, which in a sense maybe is less doubtful result that one can obtain on turbulent combustion. Starting with the Kolmogorov law for the inert turbulence, let's say the flow field is a superposition of, let's say, fluctuation with different lengths and different time. It is useful, let's say, one has the habit to consider that the turbulence is the superposition of vortices of a continuous set of vortices of dimension Li, turnover time 2I, with a relation for the turnover time and the velocity, turnover velocity, which is simply given by the ratio of this length divided the length, the dimension of the vortex divided by the turnover time. And one has a local Reynolds number, which is this the length, the characteristic length scale of the vortex is I, multiplied by this turnover velocity and divided by the viscosity, which is a diffusion coefficient, the viscous diffusivity. And Kolmogorov defined the smaller scale in the turbulence, saying that when the Reynolds number is small, he says that below this, if the Reynolds number is below that, the viscous damping stop the fluctuation. So there is no fluctuation below Reynolds number much smaller than unity, local Reynolds number. So the characteristic scale corresponding to a local Reynolds number equal 1 is called the Kolmogorov scale, and this Kolmogorov scale is a smaller scale of the turbulent flow. Where is my pointer? Ah, I have lost my pointer. Okay. Okay, here I recover. Now, so you have also in the turbulence you have also what is called the integral scale, which is defined, represented by a subscript of capital I, and Kolmogorov scale is represented by a subscript capital K. And this one, when you consider fully, very strongly turbulence, the Reynolds number for this larger scale in your flow field is much larger than 1. It turns out that simply by dimensional analysis, so you may find scaling law between all the vortices. If you, let's say vortices, it's not necessarily vortices, it's a length scale, between the length scale, in between the smallest length scale, the dissipation Kolmogorov scale, and the integral scale. When you are in between, then you may obtain a scaling law that describes the transfer from let's say vortices at a dimension at a certain dimension to smaller vortices. You have and this is the following. You know, the transfer between of energy, the energy flux, disons, across the different lengths, or let's say vortices. I don't like that because to say that vortices, because this picture is not very good. But let's say the transfer from large eddies to small eddies in this range here, in between these two extreme lengths, is just obtained by dimensional analysis. You see this, the dimension of this quantity, which is the energy transfer in Navier-Stokes equation, is simply the cube. Forget about rho. It is the cube of the velocity divided by the characteristic length of the inhomogeneity that you are considering. And if we are in steady state, this transfer should be uniform, constant. So assuming the constant transfer, and you find a scaling law between the velocity, the fluctuating velocity is the length scale of this fluctuation. And this gives you, if you call this constant epsilon, which is the dissipation range, you obtain that the V is proportional to the length. It grows, the velocity grows with the length like the power 1/3, and the energy is 2/3, and the characteristic time, which is here obtained by Li divided by V1, is also 2/3. So, and epsilon, what is this epsilon? This is a flux of energy, and it is, for example, prescribed by the internal, by the largest eddy that you know, and should be the same at the small eddies. So at the dissipation range, the dissipation now should be the energy which is transferred should be damped out by viscosity. So using that, you obtain the expression of the dissipation of this transfer transfer epsilon in term. Oh, excuse me. Where is my? Oh, okay. In terms of my dissipation range can be explained in terms of the, you know, this is new Laplacian of the velocity, which is nu v squared divided by L length k square. And this is also equal to the injection of the energy by the large scale. And the Reynolds number being equal to 1, you obtain the relation between the extreme lengths, excuse me, in terms of the Reynolds number, the power law, and the length, the time, and the velocity. What is keep in mind is that the velocity, the Reynolds number increase with, the velocity increase like the Reynolds number 1/4 and so on. So this is what is called the Kolmogorov law, scaling law, exactly. And with this, you can compute the spectrum of energy, the distribution of the energy in wavelengths, and you obtain the famous law of k minus 5/3, which is here, with the spectrum of energy distribute on the wavelengths, on the wave vector here, is k minus. And this is this spectrum of energy, in fact, is verified for 2 decades in very, very large wind tunnel. When the Reynolds number at the integral scale is, let's say, close to, let me say, close to 10,000, for example, you can verify the spectrum, the spectrum of energy in the turbulence is verified for 2 decades, at least. That's not so bad. But this is just, you know, it's not a theory. This Kolmogorov law, this is called 41 Kolmogorov's law, because there is also Kolmogorov's law later, but this one is the first, which is the most famous Kolmogorov law. And what is the definition of a strongly corrugate flame? This is only meaning for very high, fully developed turbulence, where this scaling law applies, the Kolmogorov, and we define a strongly corrugate flame when the laminar flame speed is in between the 2 extreme velocities, the integral scale, velocity at the integral scale, excuse me, here, and which is the largest one, and the velocity at the Kolmogorov scale, which is the smallest one. And when you are in between with the laminar flame speed, this defines the strongly corrugate regime of turbulent flame. There is an interesting, very interesting comment by Gibson, who was a professor at UCSD some time ago, and used by Norbert Peter, and which is what is called the Gibson scale, which is the smallest size of the wrinkle of the flame front. You know, if the characteristic length when the turnover time of the vortex is equal to the transit time across the vortex. You know, the time it takes for the flame to cross the vortex is if the velocity of the flame is when the velocity of the flame is close to the velocity of the flow at the considering scale. So this defines a scale where when the velocity of turnover velocity is equal to the laminar flame speed. In that case, you know, if think about a flame propagating in a vortex of length Li, small L, and with crossing, the time it crosses is equal to L, the length, the size of the vortex divided by the velocity of the flame, UL. And now if this is equal to the turning time, you see the wrinkle is small. So this is defined the Gibson scale, and using now the Kolmogorov cascade, you obtain that the Gibson scale is simply the cube of the laminar flame speed divided by the dissipation rate epsilon. So you have many wrinkles for in between the Gibson scale and the integral scale, and the flame take the geometry of the flame, because you have many wrinkles with different length scale as a fractal geometry. And you do not have wrinkle below LG, because in that case the flame cross this vortices with characteristic length scale smaller than the Gibson scale too fast and are no longer wrinkled. This length scale is the smallest length scale of wrinkling of the flame. So this is based on order of magnitude analysis, this consideration of fully developed turbulence. One cannot do much better. You know, fractal geometry, I just recall what is a fractal geometry just for fun. You know, it's not necessary to enter into the detail of the fractal geometry. And the fractal dimension of is defined by the variation. You know, if you consider here the surface in between, for example, you define the number NEG, the number of cube of size LG, which is smaller than LE, that intersects the flame surface in the volume LE square. So you define now a surface here, and this surface, and a fractal dimension is when this number here varies with the power law, which is larger than 2. If the power law is 2, the total, the surface of the flame is well defined, because the limit of the this ratio here, when df equal 2, goes to a constant, a finite number, and this defined is the definition of a regular surface. So a regular surface is when is defined by the fractal dimension, which is 2 by definition. And a fractal, a surface which is fractal has a dimension, fractal dimension larger than 2. So the fractal dimension can concern only scales that are greater than the smallest vehicle. So fractal dimension of a turbulent flow is meaningful between scale, in between the Gibson scale and the integral scale, right? Now, when you are in the middle. Now, concerning the velocity propagation of a turbulent flow, it's clear, thanks to the Kolmogorov scaling, that the turnover time increase with the length, with the size of the vortex, so that this tell you something, that the contamination time from a vortex to the other is simply twice the turnover time. Okay. Now, if this contaminant time, which is the relation is given here, so the fastest contaminant is due to the integral scale, because the integral scale has a velocity which is larger than all the other. So does this velocity of the integral scale is a turbulent velocity? This is right. Is a combustion time of the vortex is not longer than the turnover time, which means that if during the contamination, if during the contamination here, from one vortex to the other, you burn everything, you burn completely the things that are propagate at this velocity, then this defines the propagation. So assuming this, that the turbulence is simply the velocity of the integral scale of the velocity. You have self-similar law because you have an effective front flame at each thickness, at each scale. And at the Gibson scale, by definition, you have the turnover velocity, which is equal to UL. But if now you assume that a self-similar law, which means that the law should be the same at all the scale, the combustion time of the vortex must be equal to the turnover time. And this is in agreement now with the fact that the propagation velocity should be the integral scale. But this here is the result. The result tells you that the turbulent propagation is the integral scale of the turbulence, and the thickness of the turbulent flame is the integral scale, length scale. Now, what about the fractal dimension? Okay, if now you know the by definition the ratio of the two velocity, the two propagation is the ratio of the velocity. If you assume that the burning rate at the scale E is capital U I, is the turnover time. Now, excuse me. Now, if you use the Kolmogorov scaling, you know immediately that this, because it is related to the ratio of the velocity, is it is the power 1/3 of the ratio of the length. But dimension of fractals tell you that this quantity, the surface Ig in the scale Li, excuse me, tell you that this is by definition of the fractal dimension df minus 2. So this gives you immediately what is the fractal dimension of turbulent flame in the corrugate regime. So, and what is surprising is that these results are independent of the mixture, and experiments show that this is not the case, that the turbulent combustion and the shape of the flame strongly depend, not strongly, but depends sensitive of the composition, varies with the composition. I will skip this, which is a very interesting way, but I will skip because I have no time to discuss that. And I will finish, maybe I will not have to now. No, I'm not.
Professor, I think we have 7 more minutes.
7 more minutes? Okay.
Yeah.
Okay. If we have 7 more minutes, maybe I can finish this. Let me consider now the following problem. You see, you have a turbulent torch, which is a flame and core to the rim of a tube, and assumes that the flow in the tube is turbulent. Therefore, this flame is turbulent. That assumes that this turbulent flame is in the corrugate regime that I have just discussed. And consider the size of the flame such that the size L of the flame is smaller than the length scale of the wavelengths, acoustic wavelength. So where I am here, okay. You see, you have a turbulent flame that is going to emit sound in the free surface, and you consider the case where the wavelength of this sound, which is simply the sound speed divided by the frequency, is much larger than the flame. So this is the equivalence of what is called a monopolar sound emission when you have a volume, a ball of small volume, the volume is fluctuating. It's not difficult to obtain the flow. So you assume a spherical geometry, and you have a small spherical ball, where the volume is fluctuating. This problem can be solved to obtain the flow field, the acoustic flow field. This problem has been easily solved, and it turns out that the velocity at the distance r much larger than the flame. You say the flame is considered as localized at the origin sense, and this is the same for this for this small deformable body was with a fluctuating velocity vt. So the velocity at the point r and at time t is given simply by the second derivative of the volume, retard function by the time it takes for the acoustics to reach the position R from the origin. This is the second derivative, divided by forgetting about the 4p, AR is sound multiplied by the distance. So this is decrease, the velocity decrease like 1 over R, and the intensity is like that. The radiate flux of energy associated also, sometimes this is called the intensity of sound, but the flux, the radiate flux is simply rho v square. This is the energy per unit volume times the sound speed, because the propagation of the acoustic propagate with the sound speed. So it's simply, oh, excuse me, all right, I did a mistake. So the intensity is simply rho v square. V square is average of this time A. Now, if you want to know the total acoustic energy, which is radiate outside by unit time, you have just to integrate that across the flame, across the space. And it turns out that the sound generated by a turbulent flame, where if you call dot m the mass flow rate of burned gas in the lab frame, the equivalence of the fluctuation of the velocity, the time derived velocity here, is simply the mass flux, the mass flow rate of burned gas in the laboratory frame divided by rho b. This is the equivalence of a variation of a derivative with respect to time of the variation of a volume. This mass flow rate can be computed by a surface integral, instantaneous surface integral, divided by the velocity, local velocity or normal flame velocity in the laboratory frame, plus the flow UB, which is which flow out from the flame with the velocity, the burned gas velocity in the laminar of a laminar flame, and integrate over the surface. This is simply the mass flow rate of burned gas in associated with the flame. Now, if you use the conservation of mass across a frame, rho u, rho u, I will finish now in a few minutes. If you use this expression, you use rho b ub equal rho u ul, so you obtain this, and in such a way that the velocity, the derivative of the velocity here, dv over dt, is the mass flow rate divided by rho b. This is the mass flow rate of fresh mixture, which is divided by rho u plus the difference, the surface multiplied by the difference of velocity. Okay, I think that I am going to stop here because now I need much more time to explain the intensity of the sound. So let's stop now the lecture at that place. I will be back tomorrow with this problem. Okay.
Professor, there is a question from Thomas. Is there a good reference about the flame generator turbulence, in particular on the fuel side?
Could you tell that again? I did not pick up what you said.
Is there a good reference about the flame generated turbulence, in particular on the fuel side?
Uh-huh. For the I did not understand the turbulence generated by the flame.
Flame.
On the both side, on the
both sides. Yeah.
Good reference. Oh yes. Let's say I think that if you okay. A good reference for that. Let me think a little bit where you can find that. There is a paper. Okay, I will. I have to check my my files, and I answer later on tomorrow
Okay.
this question. Okay, because
Yeah.
I have in mind some paper, but I am not sure that the paper that I have in mind answer to this question.
Okay, so yeah, he also says that, I'm assuming he, yeah, it doesn't need by today. Later is good.
Okay.
Yeah.
Okay, I have to think to this to the question. I will give you a reference. I think that a good reference is a physical review letter paper that I have written with Louis Boyer and Jeff Serby a long time ago. But I have to check that. Okay.
Okay. Thank you, Professor.
Okay. It is finished now. We are finished. Do you have other question?
There is no more questions.
No more question. Okay.